In this video, we're going to continue with our introduction to equilibrium by doing some examples where we make equilibrium constant expressions for different systems. So a couple things you need to know before we embark on this little exercise is that when we make an equilibrium constant, we are only going to include substances that are aqueous or that are in their gas state. We're not going to include liquids, or solids. And that's because these here have concentrations that can change. Aqueous and gas have concentrations that can change. So you can change the concentration of a solution over time and the concentration of a gas over time. And for concentration of gas, we often say the pressure. But liquids or solids, their concentration is constant. So it's almost like putting a 1 in the equilibrium expression. So something times 1 is just itself. Or something divided by 1 is just itself. So we leave the liquid and solid concentration substances out because their concentration is essentially a constant value. So it's like if you have a piece of carbon and you break some particles off, the concentration of the carbon is still the same. It hasn't changed. It's still that piece of carbon or piece of pencil or whatever you had of graphite. Same thing with water. If you pour a little bit of water out of your water bottle, the water that remains is still just whatever it was before. Removing some particles does not change what its concentration was. So for those reasons, we're leaving out the liquid and solid, and we're only putting aqueous and gas substances in an equilibrium constant. So there's different types of equilibria, but let's take an example of this one here. This is a chemical reaction that's happening. We have PCl5 breaking down to form PCl3 and Cl2. And so this is a chemical equilibrium. It's an example of an equilibrium that happened. It's an example of an equilibrium that happens when you have a chemical reaction. So it's any reversible chemical reaction. That's a chemical equilibrium. So let's go ahead and write an equilibrium expression for this. We have our double arrow here to illustrate that we have two ways happening here. And essentially, the reaction will probably start off with a very high rate of the forward and a very low rate of the reverse because we don't have any reactant. But eventually, over time, the rate of forward and reverse would be equal to each other. And we could make an equilibrium expression to illustrate that. So our equilibrium expression for this chemical process is going to be K is equal to the concentration of the products. The square brackets means concentration. So PCl3 raised to the power of their coefficient, but that's a 1 there and a 1 here, assuming it's balanced, and it is, times Cl2 over the concentration of the reactants multiplied by each other. But there's only one reactant there, so we can simply put PCl5. And so what we've done here is we've created an equilibrium expression for the chemical reaction that we see here. So you can try a similar one. You can try this one over here, B. Again, it's a chemical equilibrium that's occurring. And this chemical equilibrium has the decomposition of sulfur trioxide to oxygen and sulfur dioxide. So you'll notice that all the states are gas states, which means we can include everything here in the equilibrium expression. Again, you should be pausing the video and trying it out yourself and then checking to see that you're on the right track. So if you want to write an equilibrium expression for this, we're going to say K is equal to concentration of O2. There's a coefficient of 1, so we don't really put to the power of anything other than 1, but that's implied, times the concentration of SO2, because that's the product. Now there's a coefficient of 2, so that's squared, over the concentration of SO3, which is the reactant, and there's a coefficient of 2 there, so that's squared as well. And this is our equilibrium constant, K, expression for this chemical equilibrium. Sometimes people will write KEQ. You can do that as well. KEQ, that just means a general equilibrium. You can change those letters. So for example, if you have a solid solubility equilibrium, you might write KSP. Solubility equilibrium means like the equilibrium that happens when you're dissolving something, and we'll go over that in more detail. So there's different letters you can put there, but if you leave it as K, that's fine as well, or KEQ, that just says it like a general equilibrium. So you can try this next one over here. Pause the video, then check your answer. So again, over here we have a reaction happening. We have our double arrow to show that we're likely going to head into a state of equilibrium. We want to write an equilibrium expression. So K, and that's an uppercase K, by the way, not lowercase k, because we're talking about equilibrium constant, not reaction rate constant. So we have our products multiplied by each other. Their coefficients are only 1. Just make sure your equation's balanced. Over HI, its coefficient is 2. And so that leads us to this equilibrium expression here. They're all gases, so we can include them in our equilibrium expression. And that was another example of a chemical equilibrium. We have a decomposition reaction happening here. It's a chemical reaction. Now let's go take a look at our next equilibrium. This here is a bit different. You'll notice that we're not changing the identity of the substance. We're just changing the state. So what we have here is something called a phase equilibrium. A phase equilibrium. In other words, a change of state equilibrium. So for example, we have, let's say, H2O liquid becoming H2O gas. But this can go back and forth, right? If you have it in a water bottle, you'll notice sometimes that you'll have condensation build up on the water bottle. That's because some of your water is evaporating. And then afterwards, as it hits the bottle, it starts to become liquid water again. So it goes from liquid to gas and then back to liquid. So you can have an equilibrium. That's a phase equilibrium. And you can also write equilibrium expressions for these phase equilibria as well. And so we just have to be careful, though, because we might not include everything in these equilibrium constants. So, for example, you'll see here we have a liquid and a gas. And as we learned, we only include gases in aqueous. We never include liquid or solids. So when we're writing this equilibrium constant, we're going to do K is equal to, we can put this one in, C2H5OH. And I'm going to put gas here just so we know we're putting the gas one in there, not the liquid one. And then really this here is constant. So we can essentially say over 1. So we can put over 1, but we don't really have to put that because at the end of it all, it's essentially just going to be C2H5OH, gas, like that. And that's the equilibrium constant. We do not include this because it is a liquid. So we saw examples of a chemical equilibrium here and here and here. We also saw an example of a phase equilibrium, which is just a change of state equilibrium. And the last example we didn't quite see yet, which we'll see later on, is called the solubility equilibrium, the dissolving process. And the idea is that you would take your, let's say, a solid ionic compound, for example, and essentially it could dissolve. And when it dissolves, it's not decomposing, but the ions are separating from each other. They're dissociating. So you have Na plus and Cl minus 1. And these are both aqueous since they're dissolved in water. So it's showing the dissolving process. And you can essentially have an equilibrium that happens. So when you're dissolving, some of the substance will dissociate and become the ions surrounded by water. And then some of them will reform the solid until an equilibrium is reached, essentially. Now, for a lot of these compounds, the dissolving that happens, they're so soluble that the arrow is almost only one way. But that's not super important right now. The point is that if you form a solubility equilibrium where you have your solid put in water dissociates to become Na plus 1 and Cl minus 1, your equilibrium constant would look something like this. So K, and usually for solubility, we put KSP, solubility product is what that means, is multiplied by the concentration of the ion the ions that are dissociated there to the power of whatever their coefficient is. But here they're both 1 and 1 in a balanced equation. And you would not include the solid there because, again, that stays constant as a concentration. So this would be an example of a solubility equilibrium, and we'll see more details on that later. So in this video, we did examples of various equilibria. We saw chemical, we saw solubility, and we saw phased equilibria. We wrote some equilibrium constants, and we saw the rules for how to write them. In the next video, we'll do some more examples together.